So these are all local behavior limits, and we're seeing what's happening as x goes to 0 in this case. Now, again, we have to be careful with these ones because as x, when we plug it in, as x goes to 0, we get e to the 0, which is 1, and we get 1 minus 1, which is 0. But dividing by 0, we have to be careful because we have to make sure, do we know which side of 0 we're dividing from? Okay. And in this case, it makes a difference because if we go from the positive side, we're going to go to positive infinity. Okay, so if I divide by positive 0, I get positive infinity. If I divide by negative 0, I'm going to get negative infinity. So in this case, this does not exist. Okay, so we should start kind of thinking about what do these graphs look like. Okay, there is a vertical asymptote at 0. Okay, at x equals 0, we're going to be dividing by 0. And from one side, it's going to go up to 0. And from the other side, sorry, up to infinity, and the other side is going to go down. So from the positive side, we're going to end up going to positive infinity like that. From the negative side, okay, it's going to go down to infinity like that, negative infinity. So we have to be careful which side of 0 we're dividing from. So this one here, this could be a problem as well because we're dividing by 0, but this is not some number divided by 0. This is actually 0 over 0, which we know can be anything. So this is slightly different because we have to algebraically rearrange that and simplify that before we evaluate the divide by 0. In fact, what's going to end up happening here is we're going to be able to get rid of the divide by 0. So this becomes the limit as x approaches 0, and we can cancel out those x's, so we end up with 2x minus 1. And as x approaches 0, we can evaluate the y value at negative 1. So what actually ends up happening for this graph is, this is actually a linear equation, and we have a hole at negative 1. What about this one here? This one again is a 0 divided by 0. So the fact that we're going to 0, we have to clear up this 0 divided by 0 issue first before we even worry about which side of 0 we're coming from. Okay, so this is a 0 over 0 situation. So we've got to clear this up first. So how can we clear up something like this? Well, we can rearrange this expression to look like this. X plus e to the x plus 1, e to the x minus 1. Because this is actually a difference of squares. And when we write out the denominator, we can see that those cancel out. Now, if we try to evaluate it, well, plugging in 0, well, I can actually now evaluate this as a number. So e to the 0 plus 1, well, that's 1 plus 1, that's equal to 2. Okay, and I don't know exactly what this graph looks like, but we should maybe graph it and take a look at it, and we can see what this looks like. Okay, and why that, and we will know that as it approaches 0, it will hit y equals 2. In fact, we do know what this looks like actually. This is just an exponential function that goes through 0 and 2. Okay, so this is positive 2 through that point. Okay, so those are local behaviors. These are endpoint behaviors, which they tend to be a little bit easier. For one thing, that because we're going to infinity, they are naturally a one-sided limit. You can't approach an infinity from both sides. You can only approach it from one side. So when we look at endpoint behavior, we can talk about strong over weak. Okay, and that's a very easy argument to use. Here, we can simplify this, just like we did before. But we could also say, well, this is quite a bit stronger. So if you can recognize that, that would be useful. But we could also simplify this algebraically. So there are a few different ways now that we can analyze this limit. Okay, so I'm just going to do the algebraic simplification and then plug in infinity into my limit. and we can see that it ends up going to infinity. Okay, and again, this is the same graph. We can see that, yeah, it's going to shoot off to infinity as x gets large. And that's different than the local behavior that we're seeing here. Here again, we can make an argument. These are equivalent powers. So we can say that all the other powers that are below it are insignificant compared to the x cubed, because infinity cubed is way bigger than just infinity. So we can just say then that these terms become insignificant. Okay? These terms become insignificant. We just can compare this ratio. So the limit works out to be just 5. Okay, so we'll have a horizontal asymptote at y equals 5. This next one, well, we've got a squared here, cubed here. Well, that's definitely, the denominator is more powerful. But we have to recognize that this exponent is the most dominant expression in this expression, or the dominant function in this expression. So if this is the case, here we have definitely strong over weak. Okay, so this case, that limit must be infinite. Here we have the opposite. This log x is a very weak function. As we go to infinity, and again, this strong over weak only is good for this endpoint behavior. But as we go to infinity, we have weak over strong. Okay, so if we have this weak over strong situation, that's always going to go to 0. Okay.